Okay, welcome everyone to the INQA online seminar for today, October the 8th. And today's speaker, I'm pleased to say, is Jaka Vodeb from the Jülich Supercomputing Center in Germany. And Jaka will talk to us today about stirring the false vacuum by interacting quantized bubbles on a 5,564 qubit quantum annealer. Over to you, Jaka.
All right. Yeah. Thank you, Paul, for this nice introduction. So hello, everyone. So what I'll be presenting today is really it's a collaborative effort, as you can see from this list of authors. And well, most of the authors are, like Paul already said, from this Jülich Research Center in Germany, including myself. And then there is also this one of the bigger contributors is Jean-Yves, who was at Leeds and is now moved to Austria, to the Institute of Science and Technology. And yeah, also Andrew and Zlatko are part of this team. So yeah, I really owe a lot to all of these authors for making this work possible. So, all right, let's get into it. So what we'll be studying is this transverse field Ising model in a longitudinal field. So maybe for anyone, if they happen to be unfamiliar with this, I'll just go through it. So basically this term is responsible for the interaction in our system. And as you can see from its structure, it's an interaction between a chain of spins, right? So these neighboring spins on a spin chain interact with each other. And the way it's set up is that the interaction is ferromagnetic, so that they want to be aligned with each other. And you have, so if you include also this transverse field term, which is in our case responsible for the dynamics of the system, then you have these two states, a superposition of these two states, like all polarized up and all polarized down spins. This is the ground state, right? And then what we'll be focusing on is if we introduce this longitudinal field, which will be time dependent, then we can bias one of these ground states, right? So for example, if I align HZ, the longitudinal field, to be pointing down, then this is the ground state, and I'll be calling this the true vacuum. This has some relation to cosmology. And then the other state, which sort of is thrown out of this previous superposition, will become a metastable state, a so-called false vacuum state. And then the basic question essentially is, if I start from this state of a false vacuum, how will I get to this true vacuum state? And the answer is, just to flash it already, it's through these so-called quantized bubbles, where you have a bubble of a certain size, a quantized size, for example, n spins. Within this bubble is a true vacuum bubble, and then it's in the background of this false vacuum, right? And the way we will be doing this on an actual quantum annealing device, a D-Wave device, is through this protocol. And how this will work is, at time 0, you first manually sort of program all of the spins to be in this polarized up direction. So you basically prepare this false vacuum state. You force it to be on the device initially. And at time 0, this HX field is 0 also. So then you turn it on in a certain time frame. And then you also, at the same time, you also keep this HZ value, which is plotted on this axis here. You keep it so that it's aligned with this false vacuum, just to make sure that you are still forcing this state for the purposes of this initialization process. And then here at this point, the initialization is sort of over. Then you pause the HX field for some time, and this is the time that will be plotted on all subsequent points. This is the time of our time evolution of our system that we are interested in probing. And during this time evolution, we also flip this HZ field to basically misalign it with this initial state, right? And in the end, it's pointing down, so in this minus direction, right? And essentially, we are then in the end of this time evolution, we have to turn the HX field back off to 0, and we measure the configuration of spins from the device, and we see what we get, right? And we vary this time evolution, this pause time, right? This will be, if this is 0, then you just do the initial ramp and the final ramp, and you say that time is 0 in this case, right? And then you just prolong it so that you see what is happening during this flipping of HZ. Okay, so this is, let's say, the initial setup. It's possible to map this transverse fieldizing model in a longitudinal field to this standard form that is used by D-wave quantum annealers. So essentially, if you factor out this B here, then A divided by B gives you the HX ratio, right? And then you can use this time-dependent bias feature that's now available on the annealers. You can use it to get this time-dependent longitudinal field. And the interaction is just basically a straightforward mapping. And what we used is this D-wave advantage. So it's not the newest one, the advantage 2, but it's the slightly older one, which still has a bigger chip to it. And this is the image of the whole chip. So all of these over 5,000 qubits. And what we managed to do, this is like a zoom in of this small area, right? You see here in this inset, we managed to embed, so each qubit represents a spin in our spin chain. And if you sort of follow along in such a pattern, all of these qubits, then you can make this really, really long chain throughout the whole system, which is 5,564 spins. And it's also, here you can see, closed. So it's it has periodic boundary conditions, right? Okay, so now let's move on to after this initial setup. Now that we know which problem we'll be addressing, let's try to sort of think through what we expect to happen in this model, right? So if we take this extended transverse fieldizing model and we just write this sigma z part of it, right? This is usually on D-wave devices denoted as AHP, like the problem Hamiltonian, but this is just notation's sake, for notation's sake. And what you can do with this term is you can define in a standard way this magnetization, which is just a sum over sigma z's, and it can go from minus the number of spins n to plus the number of spins n. And you can also define the number of kinks, right? Which is a little bit more complicated, but essentially what it measures is the number of domain walls or kinks in your system. So when you have two neighboring spins, one is up and one is down, then this boundary between them is a kink, right? So this state, for example, has magnetization n, right? Because all spins are pointing up, they are all positive. And it has 0 kinks. And then this state has magnetization 0 because all spins cancel out. And it has n number of kinks, so the maximum number. Like for every spin, there is 1 kink in the system. Okay, so after we do this, then we can rewrite this term into such a simplified form, right? The interaction term basically becomes the number of kinks, and this longitudinal field term becomes the magnetization, right? And then why this is useful is because then you can plot this whole Hilbert space of this Hamiltonian into such a simple 2D plane, right? It's just useful to think with. So the x-axis will be magnetization, the y-axis is the number of kinks. So for example, our initial false vacuum state, this all spins up state, is here, right? So this is a system of just 10 spins. So this state will be like maximum magnetization state. And this number here next to it, the number 1, denotes that there is just one state present at this point here. So then if you sort of follow this through, this idea, then you can plot all of the other points in this Hilbert space, which is the important point to sort of emphasize here is that this Hilbert space is discrete, right? These points don't go continuously one from to the other, but you really have to have these discrete jumps because you are simply flipping the spins in the chain, right? So then if you think a little bit further, right, then you say, okay, my initial state is this state here in this part of the Hilbert space. And even if I turn on this, the HX field, right, to induce some dynamics in my system, then if this state is the only one at a certain energy, then no dynamics will happen, right? Because it's just an eigenstate of the Hamiltonian, so nothing will happen, and that's correct, right? But then, if you think a little bit further, then what you can do is you can check again this Hamiltonian, and you can vary it with respect to the number of kinks and the magnetization, right? So, and then you set this variance to 0. In order to find these so-called equipotential lines. So basically lines throughout this Hilbert space where states have the same energy if you can connect them with such a line. And then you get this formula where you have this slope of the line, delta kinks divided by delta magnetization, is related to this ratio of the longitudinal field divided by interaction, right? And if you set this J to 1, just to set the energy scale, then this HZ essentially tunes the slope of the line. So one example, the simplest one is if the slope is -1, then this is this line, for example, right? And with this line, if it's the initial state, then you can connect all of these other states with it, right? So all of these states in this Hilbert space have the same energy as the initial state. So now what this means is that even if you turn on the HX field slightly, infinitesimally small, all of these the eigenstate will be some superposition of these states, and then you will have some dynamics, right, compared to the previous case. And then you can see how, so this is the first case, and then if you can also have many other lines, right, which are all of these green lines, which have to have these discrete tilts, right? These discrete slopes, which are tuned by HZ. So basically, at some discrete values of HZ, some quantized values, you will have some dynamics, and at all of these other slopes in between, for example, you will have no dynamics, right? Okay. So hopefully this is clear. If there's any questions at this point, maybe. Okay, so this is
a quick clarification. Maybe I see a blue line on the left-hand half plane at
this
a
one.
slope. Yeah, what is this?
It's just the boundary of the Hilbert space. So
Okay.
So nothing outside of this triangle is in the Hilbert space.
Cool. Thanks.
All right. So all of this, what I said, is then summarized nicely in this relation that this HZ has divided by 2J has to be -1/n, right? And this n is just an unnatural number. So like 1, 2, 3, 4, 5, and so on. And this n tells you the size of these quantized bubbles, essentially. But we'll get to this. All right. So one example, right, which I've already sort of shown, is this hz equals minus 2j resonance, so the slope is -1, right? So then basically if you have the initial state, this all spins up state, then only such states like drawn here are participating in this resonance. So essentially it's basically just states with single spins flipped, right? So these are so-called one bubbles, right? One spin bubbles. And then you can move on to the next one, right? The slope is -1/2, so hz equals -j. Then the closest state here has not a single spin flips, but you have to have two spins flipped simultaneously. And then these sort of next order states that are further away have larger bubbles, as you can see, like 3 bubbles and 4 bubbles, and then also single spin flips. But we'll get into this later. These are this is due to some so-called interaction effects between different bubbles, right? But this is just to show that what kind of structure these resonances have. And then what we can measure, just to be clear for the subsequent plots, so we measure this bubble density, lambda n, and the n is the size of the bubble, right? So for example, for a fully polarized state, all bubble densities are 0, right? There's no bubbles. But in this case, you have a single 2 bubble, so then lambda 2 is something that's not 0. And then further on, you have lambda 3 here, for example, is non-zero, and also lambda 1 is non-zero, right? So 1 bubble density and 3 bubble density, and then so on in this case. Okay, so this has been a lot of, let's say, more theoretical talk, right? More just pictures and then hand waving. So now let's get into actual results from the device. So what happens if you actually try this on a quantum annealer, right? With these 5,500 something spins. So what we did is this sweep through these different endpoints of hz, right? So we go from 0 to -4. And as expected, at hz equals -j, right? This is the 2 bubble resonance. You see this very nice peak. And then also at the hz equals -2 resonance, you see also another peak, right? So just to be clear, here I'm plotting magnetization, right, on this this heat plot in this z-axis, and I have 2 scales. So one is from -1 to 0.999. This is basically all of this region, and then from 0.999 to 1, this is just other region, right? So basically the 2 bubble resonance has to be resolved on the 4th decimal of the magnetization. But in any case, you see both of the resonances very clearly. And also here up top, you see something that also looks like a resonance, but it's related, it turns out, to adiabatic dynamics. So essentially, just to show here, when the hz, maybe I'll show this later. So when hz initially changes from this positive value to a negative value, then already initially the false vacuum state is sort of following an instantaneous eigenstate at these large hz's. So this is why you get these sort of adiabatic dynamics. So you change essentially the initial state, and then you get some other effects which are not really related to these resonances that I was talking about before. But it is more besides the point. So here, for example, what we see is an example of some measured spin chain states that we see from the annealer. So here we have an initial state where all spins are polarized, and then radially the hz magnitude will increase. So at low hz magnitudes, you see these large bubbles. Like here, this is an example of a 300 spin plus sized bubble. And then when you increase hz more, then you see smaller and smaller bubbles, which is consistent with the theoretical prediction, which essentially says that the smaller hz is, the larger the bubbles are, right? This 1/n correspondence. So then these plots here below show the bubble density that I was talking about before, this lambda n. And these lambda n's are shown in different colors. So lambda 1, so the 1 bubble density is blue, and then the 2 bubble density is orange, and 3 bubble density is green, and so on. And here I show basically plots at different hx values. So essentially what hx tunes is the rate of dynamics, right? Like how fast any kind of dynamics in my system are. And at these low values, you have the fastest resonance, which is the 1 bubble resonance, because it turns out that the rate of dynamics is basically proportional to hx to the n power. So this resonance is the fastest, and you see it at the lowest value of hx. And you see around this peak, which is at hz equals -2, right, where you would expect the 1 bubble resonance, you see the largest density of 1 bubbles. You also see this weird shape, right, which is essentially because of thermalization effects. So if you leave this on for, if you observe the dynamics for 2 microseconds, this is quite a long time. So this is here at this point. Then these 1 bubbles basically start to decay into 3 bubbles and 5 bubbles, which is also a bit peculiar because you don't see any 2 and 4 bubbles. But this is also a little bit besides the point. And then the next resonance, right, the 2 bubble resonance, you see this is an example of a very nice peak where you only resolve 2 bubbles and all the other bubble densities are 0. The reason why it's offset a little bit is simply because it's shown here. So when you tune hz on the device, that let's say the target value is -2, essentially what happens when it approaches -2, it overshoots, right? It does this sort of modulation. It doesn't hit it perfectly like it should, but yeah, it's due to some noise filtering effects that are implemented on the device. But yeah, so essentially this is the reason why you are sort of hitting the resonance already before. It's because you're overshooting with hz. But yeah, as you can see also from this plot nicely, the bubble density in time, right? Because below I show bubble densities when you sweep through different hz values. Here I show the dependence versus time. When you tune to this 1 bubble resonance, you really see how 1 bubbles shoot up the most because they should be dominant here. And they are really governed by this modulation, right? So these bumps in the density are really due to hz. So these are essentially hz-driven dynamics, right? It's very clear from this plot. And then when hz settles after some time, here is where you can immediately see how these start to sort of decay, right? The 1 bubbles decay and then the 3 bubbles go up. And this is the thermalization effects I was talking about before here. So then let's just finish up this slide. So you can also see lower resonances, 3, 4, 5, 6 resonance, where you see these peaks, which admittedly, they're not as nice and sharp as this one, where you only have for example, here just 3 bubbles. It's a mix of 3, 4, 5, 6. So the reason for this is very simple, because when you sweep hz from some positive value to some negative value that corresponds, for example, to the 3 bubble resonance, then you're also sweeping through all of the previous resonances before getting to the target value. And if the time scales are sort of similar, and if hz is moving kind of slowly through the resonances, then you also get the other resonances sort of involved in the dynamics, right? So this is why we see more of them. And this is just to show the last plot, what is the highest resonance, the largest bubble resonance that we were able to resolve nicely as a peak, is this 6 bubble resonance. Yeah, 6 bubble resonance. Okay, and yeah, here you can see how you can increase HX, how you have to increase HX really by quite a lot if you want to even be able to see these bubble densities, because the dynamics of 6 bubbles are so much slower than the dynamics of 1 bubbles. Okay, so maybe let's now turn a bit away from the actual results from the device back to theory, because we really did some nice analytical calculations on what is happening. Let's say if you assume perfect Schrödinger dynamics in your system, you can do this Schrieffer-Wolff transformation, which is when you know the relevant energy scale, it's sort of like doing a perturbation theory around this dominant energy scale. And in our case, we know where the resonances are, so we know basically which states participate in our dynamics, so we can do this. It's relatively straightforward then once you know this. And the point of these Hamiltonians is just to show how they look like, these effective Hamiltonians at different resonances. I won't go through all of this. I'll just show this in the pictures, because I think it's much nicer to go through, much more understandable. We have here the 1 bubble resonance, so what is happening here, and here we have the 2 bubble, and actually it really counts for it counts for like higher resonances also, so like 3, 4, 5 bubble resonance. It's also the same picture, you just have to increase the bubble size. But yeah, so the 1 bubble's resonance is a bit special, because here what is happening is first you have the initial state, the false vacuum state, and then what can happen is you have this effective Hamiltonian that's proportional to hx, so hx to the 1 power, right? And the first thing that happens, the first order effect, is that you get the creation of these single isolated 1 spin bubbles. And then these guys can actually move like free particles. They can hop from side to side throughout the system. So this is shown here, right? This guy moved from one side to the right, just to show it can hop. And then, of course, later on, more bubbles can form in your system, right? And these guys can also move around. And then in the end, basically, you end up with like a gas of these free bubbles, but the way they interact with each other is that they bump into each other, right? So it's like sort of hardcore bosons on a chain, right? And then in the, let's say, general resonance case, here it's just the 2 bubble resonance is shown just for clarity. You have the initial state, then you have these 2 bubbles forming, right? Here's one example. And these guys, in contrast to these 1 bubbles, 1 spin bubbles, are fixed. So they cannot hop around the system. We've shown this analytically that it's forbidden. And of course, still, what can happen is that you get another neighboring 2 bubble forming in your system. And if it happens that these 2 guys are neighbors with just 1 spin separating them, then they also interact. And this is how the dynamics then progress more towards the true vacuum, where then what happens is that this guy, the left bubble, steals the spins from the right one, or it could also be vice versa, of course. So then you have basically a larger bubble, a 3 spin bubble, and a 1 spin bubble also left. And this guy then again can move around the system, and this one, the largest one, is also stuck. So then in the end, what you end up is this gas of sort of the resonant bubbles and also larger bubbles, which form because of interaction, and these 1 spin bubbles sort of whizzing around the system like free particles. Okay, so this is shown here nicely in this plot. So when you tune to the resonance, you see first the 2 bubbles density goes up, and immediately following is these interaction effects where you see also 3 bubbles forming in your system and 1 bubbles. And then this next order effect after quite a long time, like an order of magnitude. You see also 4 bubbles rising and 5 and so on. And then we checked if this also happens on the annealer, right? So this is a nice question to ask. Here, these are, like it says here, MPS, numerical emulations of about 100 spins. So we also input the actual experimentally measured HZ dependence, right? So it looks like this modulation. And as you can see, these resonances are really sensitive, right? So when you're trying to tune to the HZ equals -1 resonance, which is this dashed line, then as you can see, the bubble density basically does nothing until the HZ sort of hits the resonance point exactly. Then you see all of a sudden the bubble density sort of shooting up, and it has these dynamics, right? Then it's sort of stationary, and then only when it hits the resonance again due to this modulation, then you have more dynamics and so on. And then if you zoom in to this low density regime, then you see basically these 1 bubbles also forming as 3 according to this interaction picture. And then the question is, do we see this on the annealer, right? And the answer is yes, we do. So we see this nice modulation of 2 bubbles because of this modulation in HZ. And if you zoom into this low density regime, you also see 1 bubbles forming in your system and 3 bubbles alongside them, right? So we also see traces of these interaction effects in our quantum simulation. Okay, Paul, how much time do I have left, just to see?
Yeah, you've gone past the half hour. I'm always very bad at being strict about enforcing that. So maybe wrap up soonish, but I'm not going to be strict.
All right, yeah, no, I mean, I can wrap up, yeah, quite soon. I'm just asking for clarity's sake.
Yeah, sure, that's fine.
All right, yeah, so then I'll show just this last slide, which is essentially what we also checked, is how can you understand let's say what is happening when you hit this resonance, right? So from this numerics plot, right, and also from the annealer, it's super clear that only when you hit the resonance with the HZ field, you get some dynamics, and this is then very reminiscent of going through a Landau-Zener-like transition, where you would have 2 states involved. One of the states is the false vacuum state, so the initial state, the all spins up state, and then the second state is the one with whatever size bubble resonance you are in. So in this case, it would be the 2 bubble resonance, right? So then there's this very nice paper in PRB by these authors who have shown that this bubble density, so for example, lambda 2, would be proportional to the time of passage of this HZ through the resonance point. And there's also this hx to the power n scaling. And what we checked is just if this one is true, because we didn't check yet for different resonances, but essentially what we did is we checked, we did single spin measurements on the device, and we saw that when you have magnetization of just single spins at different magnitudes of HZ, right? So you tune it to like from 1 to -1, or from 2 to -2, or 3 to -3, 4 to -4. You see that at these large magnitudes, it takes more time, right, for the HZ to flip than it does if the magnitude is lower. I mean, it's simply because you have to go through a bigger range of HZ values, right? And then if you check how this scales with this HZ magnitude, right, you see that the time it takes for these curves to reach 0, it scales with the square of the magnitude, right? So this is just it's just an artifact of the device basically, but it's nice to know because if you take the two-bubble density, for example, the time dependence of it, and you plot it for different HZ magnitudes, this is essentially like plotting it at different speeds, time of passage, right, through the resonance. And then you see when you collapse, when you multiply the time axis with the square of the magnitude, you see this very nice collapse of these curves onto a single curve, which is very reminiscent of this sort of Landau-Zener-like behavior, right, according to this law. So yeah, I think with this, it's just a nice way sort of to think about what is happening near these resonances. And I think with that, I think it's time to conclude, and I would like to thank you for your attention.
Thank you very much, Jaka. Lots of interesting things to think about there. And I will now offer this up for questions. So if anybody has any questions for Jaka, please either speak up or raise your hand or turn your camera on or whatever. Hurry, you have a question.
Hello, thank you very much for the very interesting talk. I have just one question. How do you project a realistic, potential of a scalar field, let's say, to this Ising model? Is it through the HZ, variation of HZ, or how do you do this?
So I'm not sure I'm clear on the question. The question is, how do I project?
Because for instance, I'm a cosmologist. Okay, in cosmology, you have, for instance, an inflation model has a special form of potential with a false, for instance, vacuum and a true vacuum. Now the potentials can be very different. The dynamics, if you like, would be very different. Now, if we want to project this, simulate this in such annealer to see how it works, how should the parameters and so on of the potential be projected to this Ising model?
I see. Okay. I think I understand now. So basically the question is like, how can I change these? So if I have this Hamiltonian, right, which I started with,
exactly,
then like how does this HZ parameter and maybe the interaction, how will it impact this energy landscape, right?
Exactly.
Yeah. Okay. Yeah. So I think the answer is twofold. So first of all, when I pick such a model, then the interaction or the potential landscape is very fixed to something that looks qualitatively like this, right? You just have these two sort of minima, and one is the local minimum and one is the global minimum. But then if you want to introduce more complex potentials, then you would need to do really more, I think, a completely different definition of the Hamiltonian, right? So it wouldn't be enough to have just such a simple form. This is like, like you can imagine, this is the simplest possible way of making such a two minima landscape. But then what you can do is you can essentially program your quantum annealer, like a D-wave device, so that you encode like a spatial coordinate, which you would need to encode some field in some field theory. You can encode this coordinate as like different strings of these Pauli matrices. And then with this, then you can use this more general interaction term between them to encode actually whatever kind of landscape you would like. So you can really be arbitrary with this. But yeah, unfortunately, I think I would need here like a really, there are papers on this. People have already done this. so I don't know, maybe I can also redirect you to these papers, which are actually quite nice in doing this, from which also use the D-Wave device to some degree.
Thank you very much.
More questions for Jaka? Maybe while we have this slide in front of us, in the top line, your ferromagnetic interactions time independent, but in the second line it's time dependent. Should I care about this? Does that have some subtle effect, or is that?
No, it really is time independent, even though here it looks like it is. And the reason is quite simple, is simply because when you here at this point, so the initialization ramp and the measurement ramp, right? I completely agree with you. It's not time independent, right? But if I fix it, right, the A and B at this point, then it is time independent, right? Because at this point where hx is fixed, at this pause, then A and B, so in this slide, A and B are also fixed, right? So that's essentially how you fix the interaction. And the only problem is if in the initialization, right? So if in the initialization, you would sort of ruin your desired initial state, which is this polarized state, then it's a problem. But in this case, it turns out that when you do it, even though you turn on hx for to some small value, right? So these A and B's are changing throughout this ramp. Because this A is so small compared to B, the initially polarized state stays the same basically throughout the ramp.
Good, yes, thank you. Viv, you had a question.
Yeah, it's probably a crazy question, but I've played with changing dimensions of systems in a quantum walk setting rather than this. So you've embedded an enormous spin chain on here, and essentially you're playing with a one-dimensional model. What changes or breaks if you put some crosslinks in between bits of the chain? Or is there something higher dimensional you can do, which I suspect would be fundamentally different?
Yeah, so a generalization just simply in this model, right? So that the interaction is not in a chain, but within a square lattice, for example, right? 2D case. This is, of course, yes, interesting to study, right? And even 3D in principle is doable on D-Wave. And well, since it's such a good question, I'll just show some results. But this is unfinished work, so I didn't really want to focus on it too much. But the story essentially remains very similar, but you're on a square lattice, right? For just as a simple example, right? But you're doing the same thing as in the 1D case. And then what happens is you still have these resonances. So for example, when you tune, but the values of hz you have to tune to are different now. It's not the same values, right? So for example, if I tune to hz equals, well, it should be minus 4j, but doesn't matter, like 4j, you get only single spin flips happening. So this is how the false vacuum decay would look like. Only single spin flips would occur randomly in my system. When you tune to 3j, you can only flip 2 spins at a time. So you would have these pairs of spins flipping randomly. But what's really interesting is the 2j resonance, which is even if you have a single flipped spin randomly, and actually you can flip 4 spins at a time, just randomly, then what happens is that if you add on to this already existing state a single extra spin, it costs 0 energy, right? So what happens is you have this sort of spreading of this false vacuum throughout the whole system, essentially for free, right? All of these states have the same energy. So yeah, there is this fundamental difference, let's say, but I would say it's at least to me it was quite unexpected, right? I didn't expect this to happen because it doesn't happen in the 1D case.
Now, so was Jaka involved in, and his collaborators involved in this work also, because this looks very much like topological protected states?
Sorry, can you repeat the point with the collaborators?
So Zlatko Papage from Leeds.
Yes, yes.
Was he involved in the 2D work also?
No, so now we are working on the 2D case now. We finished up the 1D case. It's already written up in on archive. But yeah, the 2D case, we're working on this now, but he was also involved in the 1D case. Initially, I brought him on sort of because he has a lot of expertise in these 1D PXP models, if you're familiar with this.
No, but I'm familiar with the work that he and his collaborators at Leeds do on topological states for quantum computing. And the fact that you have stuff like that is all at the same energy reminded me of some of the stuff they do with that. That's why I was asking. But yeah,
yes.
Fascinating system to play with. So I'm looking forward to more results. Thank you.
Yes, thank you.
Okay, I think we should probably conclude there in the usual fashion by thanking Jaka once again for an excellent presentation. Thank you, Jaka. So I remind you there's no online seminar next Tuesday, but we return in 14 days' time with the next online seminar. I'm afraid I can't remember it. I'm sure it will be another excellent presentation. So I look forward to seeing you all then. And thank you once again, Jaka.
Yeah, thanks. Thanks, everyone.
Thank you. Bye.